Happy Saturday, scientists. Let's review. Today is all about motion as we do the forces topic. Let's move on into it. We've gone through these methods for measuring speed and distance, or time and distance, and the reason that we want to do that is because the equation that we're using for speed is equal to the distance that was traveled divided by the time. In science, this is usually meters and seconds, but in the real world you might see kilometers per hour. You might also see miles per hour. All of these things are rates, so whenever you hear the word per, you need to be thinking about division. We need to talk about how we go about converting between different units. And one of the ways that we can do this and ensure that we do it correctly is to apply something called unit analysis. In order to do this correctly, we need to know a few mathematical truths. You need to know that if A is equal to B divided by C, then you can switch the positions of A and C without changing the equation. So C would be equal to B divided by A. And if you don't believe me, try it with some numbers. 3 is equal to 6 divided by 2, and 2 is equal to 6 divided by 3. And this is going to be quite useful for us. Another thing that we need to know is that A divided by B divided by C is the same thing as A times C divided by B. We can flip that bottom fraction and put them together. The final bit of mathematical truth is that A divided by A is equal to 1, and in an equation we can ignore it, because we know that 1 times something is just that something. What we usually do in an equation is we say that A over A cancels each other out. When you combine all of these things together, you can do unit analysis properly. What you're going to have is some form of starting unit, and you'll multiply it by some form of conversion factor in order to end up with some final desired unit. Let's use the example of turning 60 seconds into some number of minutes. Now you can probably do this in your head, but I want you to think through the actual process that you're doing. If you have 60 seconds, you have the unit seconds on top. We need to get rid of that, so we need the unit seconds on the bottom. And we have the unit minute on top, so we need to have minutes on the top. Now we just need to figure out what the conversion factor is going to be. And we know that a minute is 60 seconds, so the 60 goes down below and the 1 goes on top. 60 divided by 60, which is what you really did in your head, gives you 1 minute. And this will apply for any unit conversion that you're doing. In this unit, there is one that does come up a lot, and that is converting something like 36 miles per hour into some number of meters per second. So let's go through and decide on our conversion factors. Well, if we have miles per hour, what we're really looking at is miles divided by hours. So at some point in time, we're going to have hour on the top and miles on the bottom. Let's start by doing that. Let's put our miles on the bottom, and then we need to end up in meters. We need to remember that conversion factor, which is 1,609 meters for every mile. Next, we're going to need to convert from hours into seconds, and we see that hours is on the bottom over here, so hours will have to be on the top up here. Seconds is on the bottom here, so seconds will need to be on the bottom there. Now, you can do this in two ways. You can remember that an hour is 60 minutes, and each minute is 60 seconds, and so you can kind of do a mini conversion within there, or you can remember that it's 3,600 seconds. The equation that we're actually doing is 36 miles times 1,609 meters, and then that answer divided by 3,600 seconds. However, I recommend that you actually put it into your calculator with these fractions, obviously not with the units, but then you're able to find out what your correct answer is, and you really make yourself understand the process that you're going through. And when you do this, you end up with 16.09 meters per second in this particular instance. Our next topic to discuss is the difference between a vector quantity and a scalar quantity. A vector quantity has a magnitude, that is to say a number, and a direction, whereas a scalar quantity just has a magnitude, just a number. There are a few common examples, and so we'll do a table that has vector and scalar, and then we'll put in the equivalents in each. In the scalar side of things, we have distance, which would just be something like 5 meters away. In the vector quantity, you have displacement. And this is a way of measuring both how far away something is, but in what direction. It's probably more useful if you're giving someone directions to give them 5 meters north versus giving them 5 meters. In the scalar quantities, you have speed, 20 miles per hour, and in the vector quantities, you have velocity, 10 miles per hour north. Again, you have a direction associated with that. Sometimes in the vector, instead of using a direction, you'll use positive and negative, and then you'll be referring to grid coordinates in terms of what positive and negative actually mean, and sometimes you're referring to an actual direction. There's one more that is not exactly equivalent like these previous two have been, but that come up all the time, and that is the difference between mass and weight. When you're outside in the real world, someone referring to your weight is probably actually referring to what the scale says when you stand on it. However, what the scale is trying to measure is your mass. It's trying to measure the number of particles that are in your being, whereas the weight is actually the force of gravity pulling down on those particles, and so is not the same thing at all. While you're in the physics room, remember that these two are not equal. And the weight is the force of gravity on your mass, and the mass is just a measure of the number of particles. Calculating acceleration is our next topic, so let's move on to that now. The word acceleration means a change in speed over a certain time. And so to calculate acceleration, you need to figure out what the starting speed is, what the final speed is, and how long it took to make that change. We remember that calculating a change in speed means that we're calculating the end value or the end speed, and you would do this with velocity as well, minus the starting speed, and then you would divide that by the time taken. If you're referring to velocity, then you might be seeing this written as v minus u, v being the final velocity, u being the initial velocity, and then divided by time to give acceleration. Our next topic is the ways that these are represented in graphs. And the first of these types of graphs is a distance-time graph. This measures the time taken and the distance, or more often, the displacement traveled. If you take a look at an object and its distance is increasing at a steady rate, then you know it is traveling with a constant speed. If the distance is flat, then you know that it is not moving at all. And if we're looking at a displacement graph, then you might be showing it returning to its origin, whereas a distance graph, that line would just continue because we're just talking about a total distance and we don't have any directionality to it. So both of these points here, those are constant velocity or speed, depending on whether we're talking distance or displacement, because if we're talking displacement, we're talking vectors, and therefore we need velocity. And then here, that is a speed of 0, or a velocity of 0, because the line is flat. What you can then do with this is you can calculate your speed by calculating the slope of the line. you need to remember that the slope of the line is often referred to as the rise divided by the run. In other words, you're going to take 2 points on the line and you're going to take their coordinates. When you're doing this, you want to see if you can find a point that is exactly on the grid line. So sometimes that might be a 0, 0 point, but sometimes it might be a point somewhere else on the line. And then you're going to need to use the coordinates for the points. Hopefully you've seen this equation in math where you take the second y coordinate and from that you take away the first, and that tells you how much the y value changed. And then you do the same thing for the x coordinates in order to figure out how much the x value changed or how much the time changed, and then that would tell you the slope of the graph, which would tell you the velocity or the speed, depending on if you're working in a vector or a scalar world. Velocity time graphs are very, very similar to this, except in this case the slope will be the acceleration. If you take a look at this graph, this is an object that is accelerating with a constant acceleration. In section 1, we have a constant acceleration. In this second section of the graph, our object is still moving. We need to make sure that we don't get this type of graph confused, because here we're dealing with velocity versus time, and so therefore the object still has velocity, the velocity just isn't changing. The acceleration is equal to 0 for that section. And then here, in section 3, we'd have the velocity decrease. There's another thing with these that you can do, and that is that you can find the distance traveled. And that is going to be equal to the area under the graph. In order to do this, you need to decide on the shapes that are present in your graph. Here, our first area is a triangle, then we have a rectangle, and then we have another triangle again. So the total area is going to be the area of the first triangle, plus the area of the rectangle, plus the area of the second triangle. Then all you have to do is read the values off the graph, obviously using your ruler, to properly find whatever number was on the axis there, and whatever number was on the axis there, and then using your formulas for area. And remember that the area of a triangle is 1/2 base times height, and the area of a rectangle is equal to length times width. There are a number of different equations that we use to describe the motion of objects, and they are grouped into the SUVAT or SUVAT equations. S stands for displacement. U stands for initial velocity. V stands for final velocity. A is the acceleration, and T is the time. Notice that S, U, V, and A are all vector quantities. Time obviously can't have a direction to it, and so it is a scalar quantity. We've already seen one of these equations. We've seen that A is equal to V minus U divided by T, or the change in velocity divided by the time. But there are a few other useful equations, such as the fact that V squared is equal to U squared plus 2AS, and the fact that S is equal to U times T plus 1/2 of A times T squared. There are a number of different practice problems that are available to you, including some in the worksheet linked below, and so I recommend that you take a look to see if you can use these problems properly, and to see if you can manipulate these equations properly. There's one final bit that we need to know about, and that is the kinetic energy, or the energy of motion. The formula for this is that the energy is 1/2 the mass multiplied by the velocity squared, although we'll often write this as 0.5 mv squared because that's a little bit easier to work with when we are isolating with this equation. One of the things that crops up often with this equation is finding the actual velocity based on the energy. We'll go through the isolation of velocity, or the change of subject to velocity now. In this equation, you see that velocity is multiplied by 0.5 times m, which means we need to divide both sides of the equation by 0.5 m. This gives us the fact that energy divided by 0.5 m is equal to the square of the velocity. We can then take the square root of both sides of the equation to find that the velocity is equal to the square root of the energy divided by 0.5 m. If you remember that the 0.5 was actually a 1/2, and you remember our rule from earlier that dividing by a fraction meant that you could flip the fraction on its head and multiply, then you might also want to write this equation as 2e divided by m. Either of these is going to give you the same answer. And now for something related, but also completely different, the concept of forces. Very briefly, there are two types of forces. Contact force, which means there is touching between the objects, so not great in this era of social distancing, and non-contact, meaning there is no touching, or there's nothing between the objects. Common contact forces are things like friction, drag, push, pull. Non-contact forces, you have things like gravity, you have things like electrostatic attraction. That are forces where you're not actually having any contact between the object, but you would still have that force acting on that object. In theory, the next section is interacting pairs, but I actually want to come back to these after we've gone through two more things. The first thing is the concept of a free body diagram, and while this is technically on the higher syllabus, it is, I think, useful for everyone to know how we do this. What you are trying to do is you're trying to show all the forces and directions on the center of mass. To do this, you need to start by drawing the center of mass. And because we're lazy scientists, and some of us, not sure who that might be referring to, aren't very good at art, we're going to just draw a point. Then you're going to draw the forces at their proper directions, and you're going to draw them to scale. What that will mean is that you might want to take a ruler and perhaps 1 Newton per centimeter, and so that 2 centimeter force means that you're at 2 newtons. If you have forces that go off at an angle, then you would put them off at their angles, or you might have like a pushing force and a friction force. However many forces are present on that object, you'll draw them all in at their proper angle and with their proper length based on a scale, usually about 1 centimeter to a Newton, but that will really depend on the question that you're given. Speaking of Newton, Newton was the scientist who came up with 3 laws of motion, which have become absolutely critical to our understanding of physics. The first law is also known as the law of inertia. It says that an object is going to keep doing what it is already doing, or you might have heard it as an object at rest stays at rest, and an object in motion stays in motion. If we picture an exceedingly well-drawn physics textbook sitting on a table, if no one touches that book or that table, then the book is going to stay sitting on the table. Nothing is going to move it. In this case, what we're really looking at is that objects don't change velocity unless there is an outside or a net force. The book has a velocity of 0. There's no outside forces. It keeps its velocity of 0. If you start pushing on the book, then you're putting an outside or a net force on that book, and so it will start to move. Its velocity will change. If the book was already flying through space and it was far enough away from all the planets that it couldn't feel gravity, and there's nothing else touching it and there's no air resistance, then that book will continue to travel indefinitely because there is no external force to slow that book down. The Newton's second law says that force is proportional to acceleration. So it says that the force you put on an object is proportional to the mass and to the acceleration of that object. And so the first law is really just an application of this, because I always like to add under this force that it's a net force. In our example of the book, we have the normal force from the table holding it up, and we have the force of gravity, or the weight of the book, holding it down. There's no net force between there. One force in one direction, one force in the other direction. They cancel each other out because the net force is 0 and the mass can't change, then the acceleration has to be 0. If, however, we come and we push on the book with a force, then the net force is no longer 0. And so because the net force is not 0, then the acceleration cannot be 0. Newton's third law you will probably have heard as equal and opposite. What this means is that forces are always coming in pairs, and these are the interaction pairs that we referred to a little earlier. Let's use the example of gravitational force. If we have the Earth and the Moon, we know that the Moon is kept where it is by a force of gravity towards the Earth. But what we also need to understand is that the Moon is going to pull back on the Earth with an equal and opposite force of gravity. Or if you have an object that you are pushing with a certain force, then the object is going to push back on you with the same force. It's a little bit hard to understand, but it really is always equal and opposite. Equal both in type and in magnitude. So it's a gravity force from the Moon to Earth, and therefore it has to be a gravity force back the other way around. It was a push force in our example with the box, and so therefore it will be a push force back the other way around. If you're taking the higher syllabus, then you'll need to know about momentum. Momentum is a quantity that depends both on the mass and on the velocity of an object. And momentum becomes quite important in collisions because we have something known as the law of conservation of momentum. And this law says that the momentum before a collision is equal to the momentum after. And we will use this in order to study collisions. We have two types of collisions. The first type is an elastic collision. In this case, no energy is transferred to other energy stores. In an inelastic collision, there is some energy transfer. And so most collisions in the real world are actually inelastic. There's some thermal energy, there's some sound produced, there's some other losses of energy. But in terms of physics, we like to look at elastic collisions. And so you might have an example of a ball striking another ball in a snooker table, and then that ball going off with a certain speed. And momentum would help us to be able to find that speed, but you can also apply this to situations of, for example, car accident investigations or other collision investigations where you can figure out, based on where the final positions of the object are, and knowing that momentum is conserved, you can figure out how fast the original object was traveling. And now for something nearly completely different. Hooke's law. Hooke's law is all about stretching springs, and it says that the force you put into a spring is proportional to the extension. Or that F is equal to K multiplied by the extension. K in this case is the spring constant, which is a measure of how difficult it is to stretch that spring. It is usually measured in newtons per meter, which means that the extension itself needs to be measured in meters, and the force, of course, is always measured in newtons. For springs that perfectly follow Hooke's law, you'll have a lovely and perfect straight line on the graph of force and extension. However, most materials have a certain limit. This is known as either the elastic limit or the limit of proportionality. After this limit, then the relationship no longer starts to be linear, and the way that the material behaves changes. There are two sections to the graph then. There's this first section of the graph where we refer to the material as elastic. It will return to its original shape. And this section of the graph, which is plastic, where it will not return to its original shape. When you have one of these graphs, you can work out what the spring constant is by working out the slope of the graph. We've already talked about this type of equation, and for those of you who've studied your mathematics, you know that we represent the slope of any line as y equals mx, and usually plus a constant, but for now we'll ignore that. If we write out our spring equation next to this, we can see that there are some relations. The force is equal to the y, the k falls into place for the slope of the line, and then the extension, well, that's x. And what you can then do is you can work out the slope of the line based on finding 2 points on that line. Again, whenever you're doing this, you want to find points that are as nearly exactly on the grid of your graph paper as you can, even if those points aren't the start and end of the line, because it will make it easier to read those values correctly and not make a mistake. Then you'll use your ruler in order to find the coordinates of those 2 points. This coordinate here is x1, that's y1, y2, and x2. And then we know that the formula for the slope of the line, or in this case, the spring constant, is equal to the change in y, so y2 minus y1, divided by x2 minus x1. And that will give us the slope of the line, or the spring constant. So we know that a steeper line would have a higher spring constant than a shallower line. Our final concept for this topic is the concept of gravitational potential energy, or GPE. This is the energy that an object has due to its height. The formula for this is that the energy is equal to the mass of the object multiplied by the local gravity, which on Earth we take to be 10 newtons for every kilogram, and then multiplied by the height of that object. The higher or heavier an object is, the more gravitational potential energy it will have. You might be asked to isolate this equation for either the height, in which case you would divide the energy by mass times the local gravitational constant, remembering to put those into brackets on your calculator so that bid mass gets applied the way that you want it to be. You could also potentially be asked to calculate the mass of the object given the energy that it has and its potential height, and in that case what you'd be doing is you would be dividing the energy by the local gravitational constant and the height. Remember with all of these equations that really the most important thing for you to do is to take your time. You do have some time in the exam, so make sure you're not rushing. Think carefully about your units, think carefully about the formulas that you're applying, and whether or not they're correct for the question. There is a practice worksheet in the description below, and the answers to that will be up next week. In the meantime, happy sciencing and great revision.